Welcome back to Think Thrice Problem Solving. Today we're going to solve the BASEL problem. So the BASEL problem is we want to find the sum from n equal 1 to infinity of 1 over n squared. So we want to find what is this going to converge to. And if you know anything about series from the from the p-test, this does converge. And we want to find that exact value. So if you want to try this, so this actually stumped people for several hundred years. There are a few proofs that exist now. But you can pause the video and try to come up with it on your own, but you're going to have some issues probably. Otherwise, let's go ahead and look at one of the many solutions to this problem. So what we're going to do to solve this is we're going to kind of do something crazy, and we're going to look at an integral. We're going to look at the integral from 0 to pi over 2 of the natural log of 2 cosine of x dx. Okay, so pretty crazy start here. And we're going to start off by saying, so this is a 2 cosine of x is defined for 0 to pi over 2. And it's going to be greater than 0 for 0 to pi over 2, which means the natural log function is defined. So this is going to equal some value that is a real number. Okay, so we're going to be able to calculate this, and well, we may not be able to calculate, but eventually what we'll get should be a real number. I don't know what that number is, but it's going to be real. Okay. So let's look at this integral here, and let's look at this cosine function. So we're going to do our next weird thing, and I know we just said that a is a real number, but we're going to break this off and look at the complex plane. So let's look at cosine of x. So I want you to remember the how we write the exponential form as cosine of x plus I sine of x. All right, so if I wanted to rewrite this, I have e to the ix is cosine, and e to the negative ix is going to be cosine of x minus I sine of x. Okay, so if I was to add those two together, then I'm going to get 2e to the I'm going to get e to the ix plus e to the negative ix is equal to 2 cosine of x. And the signs cancel each other out. All right, so what does this mean? This actually means that cosine of x can be written in the terms of the complex exponential form as e to the ix plus e to the negative ix divided by 2. So we're going to plug that back into our equation. And now we're going to have the integral from 0 to pi over 2 of the natural log. The 2's cancel, and I'm going to be left with e to the ix plus, sorry, that's not in the exponential, so plus e to the negative ix. Okay, and now that I'm looking at this problem, once again, it doesn't look too great to the casual observer, but we're going to try to get this into a form where we can either integrate or we have some sort of method for solving. So a hint of where the direction we're going is we're going to use a Taylor series representation of the natural log. So what I'm going to do is I'm going to factor out an e to the ix in this expression. So I'm going to go 0 to pi over 2. I'm going to do the natural log. I'm going to pull out an e to the ix here. And I'm going to be left with 1 plus e to the negative 2 ix, because I just divided out that e to the ix. And then that's going to be still left here in this expression. So by my log rules, I can break this up. So I'm going to break this up now to 0 to pi over 2. And now I can write this as the natural log of e to the ix plus the natural log of 1 plus e to the negative 2ix, because I have the product of those two functions. All right, so this guy I can handle. So ln of e to the ix, so that's going to be just the integral from 0 to pi over 2 of ln of e to the ix is just going to be ix dx. I'm going to have plus the integral from 0 to pi over 2 of ln of 1 plus e to the negative 2ix dx. All right, so this guy we can take care of. So this guy on the left is just going to be ix squared over 2, evaluated from 0 to pi over 2, which is going to give me I times pi squared divided by 8. So that left one, I have an expression that's valid for that. So let's look at this right guy now. And let's specifically look at this natural log of 1 plus e to the negative 2ix. Okay, I want you to recall, and if you haven't done Taylor series expansions, then this is basically a way that we can write every, almost, well, not every function, but many functions in terms of a polynomial. So if I have ln of 1 plus y, for example, then there's a Taylor series expansion as long as y, magnitude of y is less than 1, which it is in this case because I have e to the negative 2 ix. So as long as x is in that given range, then that should be less than 1. Okay, so I'm going up here and I see ln of 1 plus y is going to be the sum from n equals, let me make sure I get this right, 0 to infinity of y to the n over n. Okay, this is actually going to be from 1 to infinity, I apologize. So our Taylor series expansion is going to be y to the n over n. Okay, which if you end up doing this, so if you take the series of these terms, so we're going to get y over 1 plus minus, and this is going to be times negative 1 to the n plus 1. Okay, so what does that mean? That means that I could rewrite this as the natural log of 1 plus y is going to be equal to y minus y squared over 2 plus y cubed over 3 minus y to the 4th over 4 plus etc. Moving down the line. And if you were to plot this, so if you go into Desmos and you plot y, then you plot y minus y squared over 2, and then you plot y minus y squared over 2 plus y cubed over 3, and you keep adding sequential terms, you'll see that this approximation actually gets closer and closer to this guy. Okay? And I have other videos where I go in a little bit more detail about how we find Taylor series. But for the purposes of this video, let's just kind of jump from there. Okay, so we have the Taylor series. But in this case, I don't have y. I have y is equal to e to the negative 2ix. So when I have the natural log, so we're going to remember that we have this guy. Don't forget about him, but I'm going to take a little more space. So ln of 1 plus e to the negative 2ix is going to equal e to the negative 2ix minus e to the negative 2ix times 2 divided by 2 plus e to the negative 2ix times 3, because I'm cubing it, divided by 3 minus e to the negative 2ix times 4 divided by 4, and so on. So I have those terms that are going to the right. What I notice here is now I'm going to integrate this. So let's go back up, and I want you to look at this integral here on the right. So I'm going to pull this down. And we're going to look at the integral from 0 to pi over 2 of the natural log of 1 plus e to the negative 2ix, which is just going to be e to the negative 2ix minus e to the negative 2ix times 2 over 2 plus e to the negative 2ix times 3 over 3 minus e to the negative 2ix times 4 over 4, and so on. So when I integrate this, I'm going to end up getting e to the negative 2ix divided by negative 2I, I'm just taking that constant out, minus e to the negative 2ix times 2 over 2 times negative 2I times 2 again. And then I'm going to get plus e to the negative 2ix times 3 over 3 times negative 2I times 3. And this will keep going. And we're going to evaluate this whole thing from 0 to pi over 2. Okay? So I'm going to bring back my whole expression. So let's look back at where I had this equal sign up here. So this whole thing was equal to I times pi squared over 8 plus now the result of the second integral. So the result of the second integral. So let's investigate. So if I have e to the negative n pi I. So if I have e to the negative n pi I, oops. So that's going to be piecewise, and it's going to be 1 if n is, let me make sure I get this right, so if n is even, and it's going to be negative 1 if n is odd. Okay, so we're either going to have that equal negative 1 or 1. So let's write this out. So let's evaluate this expression. So when I plug in pi over 2, if I plug in 1, I'm going to get negative 1 over negative 2I minus, now I have an even, so I'm going to have 1 over 4 times negative 2I plus negative 1 over 9 times negative 2I minus 1 over 16 times negative 2I, and so on. That's when I plug in pi over 2. And then when I plug in 0, e to the 0 is always 0, or is always 1, sorry. So I'm going to get plus, now I'm going to get 1 over negative 2I minus 1 over 4 times negative 2I plus 1 over 9 times negative 2I, and that's going to be minus next. 1 over 16 times negative 2I, and so on. And what we notice now is some of the stuff is going to cancel. So I have, oh sorry, this whole thing is minus, not plus right here. So this should be a minus sign. Okay, so if I take negative 1 over negative 2I minus 1 over negative 2I, that's fine. But then I'm going to take this guy, and this guy is going to cancel with him. And then this guy is going to cancel with him as we go up. And what we're going to be left with, interestingly, is going to be that same I pi squared over 8 plus, and now my entire expression inside is going to be, I'm going to factor out a little bit. So I'm going to factor out, so these negatives are going to cancel. I'm going to factor out 1 over 2I, or sorry, the 2's are going to cancel. I'm going to factor out 1 over I. And I'm going to be left with 1 plus 1 over n squared, or 2 squared, sorry, plus 1 over 3 squared, plus 1 over 4 squared, and so on. Sorry. You'll notice we killed the even term, so I'm going to actually have 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared. I apologize for that. Okay, so we're making it a little bit toward a solution here. So we have something that's a little bit funky here. So I have I in the denominator here and the numerator here. So let's multiply this by I over I. And what we're going to end up getting is that this is equal to I times pi squared over 8 minus this sum, 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared, etc. Okay, let me just differentiate these brackets. All right, so interesting. So I've kind of got to an expression here. And how is this useful? Well, let's come back up here to the top. I told you in the very beginning that this is equal to a real number. So what does that mean? That means that the imaginary part of this, so the imaginary part, which is this whole thing, must be equal to 0, which is enormous here. So what does that tell us? That tells us that pi squared over 8 is equal to 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared, etc. All right, so this is a big part of what we needed to get to. Okay, so now let's look at what am I missing here? So I'm missing all of the even terms, which is unfortunate, but there's a way we can fix that. So let's look at this. I'm missing 1 over 2 factorial plus 1 over 4 factorial plus 1 over 6 factorial plus 1 over 8 factorial, and so on. And if I was to factor out a 1 over 4, so if I take out 1 over 4, oh, sorry, this is not factorial. I was doing another video a few minutes ago. I'm going completely insane. So this is squared, 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 squared. You were probably wondering what I was doing, where that was coming from. So we're going to factor out that 1 to the 4th, or 1/4. And what we're going to end up getting is, if I factor out 1/4, this is going to be 1. This is going to be 1 over 2 squared now, plus 1 over 3 squared, plus 1 over 4 squared, and so on. So we've actually got our entire series now by dividing out that 1 over 4. But how does this help us? So if we look at this, we can see that this is actually equal to 1/4 times this same thing I started with, 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared, and so on, plus 1 over 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared, etc. Which is pretty cool. So if I look at this, now what is useful here? So I might give you a second to see if you realize what's coming out and jumping here. So now I have this guy, which I know is pi squared over 8. And then I also have this guy and this guy. So those are the same guy. So what that tells me is that now I have 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared, and so on, times 1 minus 1/4, so times 3/4, is going to be equal to pi squared divided by 8. So that means that this expression in here, 1 over 2 squared plus 1 over 4 squared, and so on, is going to be equal to pi squared divided by 24. I missed something here. Oh, the 1/4. So here we had the 1/4 outside, so this should be times 1/4. Okay, so I'm going to have pi squared over 24. So this 24 here is coming from the pi squared over 32 times 4 over 3. So why is this cool? So now I have everything I need. So 1 over 1 plus 1 over 2 squared plus 1 over 3 squared is going to be equal to my orange guy, which is my odd terms, pi squared over 8, plus this pi squared over 24, and that sum is equal to pi squared, common, so 3 pi squared plus 1 pi squared, so 4 pi squared over 24, so that's pi squared over 6. And what I've just successfully found is the sum, n equal 1 to infinity, of 1 over n squared is equal to pi squared divided by 6. So that was a little bit of a doozy, but hopefully you enjoyed the math behind it. If you did, please like this video and subscribe. If you have your own idea for a video, please submit it and you may see it in a future video. And as you're solving problems, think once, think twice, and if you really get stuck, think thrice.